Okay, in this presentation we are going to look at the difference in proportions between two populations. So we have two samples here. One sample is older people, okay, who are over 40, and the other sample is from people who are under 40. Sorry, when I say sample, those are two populations. And what we have is a sample from those populations, 400 people in each of those two samples there. So it's generally assumed that older people are more likely to vote for conservatives than younger people. So in a survey, 180 people out of 400 over 40, that's our older group, and 120 out of 400 people from our younger group stated that they would vote conservative. Do the data support this hypothesis at a 5% significance level? Now, this is a straightforward hypothesis test, so I'm going to sort of go through this one very quickly, but just to emphasize this part of it here. This is directing us towards asking, is one group greater than the other? Is there enough evidence to support that? So in other videos I was looking more at equal to or not equal to. This one actually is, I'm looking at this question in more detail about, is one greater than the other? Now, I'm going to follow a four-step hypothesis test process here that is sort of designed for critical values, okay? So this is sort of assuming that people doing an exam would have critical values, calculate critical values from statistical tables, and also presumably that they would have formula sheets for standard errors and stuff like that. So it's a very streamlined table. Probably people might sort of look at add in other remarks to that, but that is it. Just an important thing to say is that we have a significance level of 5%, and that is fairly typical of a lot of the undergraduate statistics courses that I am familiar with. Okay, so what we're going to do here is look at our hypotheses. Now, so the Null Hypothesis proposes that there is no increased likelihood in voting intentions. That is to say, likelihood to vote for the Conservatives in the older age group. Okay, so essentially, the older people are not more likely. Okay, that is a sort of a question here to sort of read back and look at this. So essentially, it is generally assumed, but actually, if you think about it, what is the right way to look at a hypothesis test? So you sort of, particularly when you're looking at the null hypothesis, so you will sort of assume a very strict, neutral point of view until there's strong enough evidence to change that point of view. So usually, when you write out null hypotheses, you sort of say no difference, no increased likelihood, nothing's different from each other, okay? There's no significant difference from one group to the other, okay? And that's always sort of expressed in the null hypothesis. So what we have there, actually, what I have highlighted here is actually more of an expression of the alternative hypothesis, okay? Now that's a sort of important sort of element of this particular question, the way it is worded, because the alternative hypothesis, we would sort of always suggest no difference, something is not larger than the other, something there's a lack of any interesting characteristics, that sort of thing. That would always be sort of expressed in the null hypothesis, okay? So how we might phrase that mathematically, or denote that mathematically, where here group 1 is the older people, okay, and 2 is the younger people, and pi is the population proportions. It's not larger is the same as saying it's less than or equal to. So not larger is what we would typically put in the null hypothesis. And how you would phrase that mathematically is less than or equal to. But less than or equal to is actually the same as saying not larger, okay? So you can actually, that symbol there, less than or equal to, you can actually just rephrase that as not larger than, okay? So people less than or equal to, that's how you sort of might verbalize it immediately, but let's just reverbalize it or come up with a new verbalization for it as not larger than. Okay, that would sort of help you. So pi 1 is not larger than pi 2, okay, or pi is the population proportion for older voters and pi 2 is the population proportion for younger voters. The alternative hypothesis is that pi 1 is greater than pi 2, which is to say that the population proportion for the older voters is larger. This sentence here is a sort of template sort of text really for all types of question. So in this case, we're talking about two age groups and two proportions with regard to voting for a conservative political party. But this is the general form an alternative hypothesis should take from question to question. So you just might rephrase that or add details to that, but that should be the general theme of your alternative hypothesis. And again, the alternative hypothesis is where you would make a statement about a difference, or you would say that something is larger than another. Okay, that's where an expression of a significant difference, expression of a significant characteristic of the data, or something special is seen in the data. That's where you would write that in the alternative hypothesis. Okay. Now, I'm going to rephrase those in terms of differences. Okay. So, just a quick mathematical statement. Pi 1 minus pi 2 is not greater than 0. Pi 1 minus pi 2 is greater than 0. Okay. So so a little statement like that: older voters are not more likely to vote Conservative. Older voters are more likely to vote. Okay, that is something like that is what should appear in your exam paper. Okay, now I have it bunched in there, but take your time at it because it's one of the 4 steps. It's a key one. And in a lot of questions, you're actually asked to state your null and alternative hypothesis clearly. Okay, I didn't really ask that particularly specifically in this question, but that is what you have to do. Now, something that is particular to this particular video that I haven't done in other videos is that this is a two-tailed test. Sorry, a one-tailed test. In a lot of videos, I would work on the basis of a two-tailed test, but in this one I am working on a one-tailed test. How do I know it is a one-tailed test? Well, essentially I'm looking at this greater than or greater than 0. So it's this operator here. Okay, so it is the null is less than or equal to, and the alternative is greater than. So it's essentially how many alternatives to the null hypothesis does the alternative offer me, and it's a 1. Okay, that's just a sort of rule of thumb to remember how how many tails in the test. Just another quick remark: the equality component should always be in the equality operator should always feature in the null hypothesis. So that is, again, we'll go back to this. Not greater than is the same as saying less than or equal to. They should always have the equality operator in the null hypothesis on this side, never on the alternative hypothesis side. Okay. Now, that's the main part of this work done, really. Actually, that's the key part of this video. So the rest of it is actually number crunching and then looking at the critical value and so on. So the point estimates are as follows. I'm going to run through this very quickly. 45% for the older voters, okay, and 30% for the younger voters, okay, who would vote for the Conservative Party. And our point estimate is the difference between these two proportions, which is 15%, okay. So the standard error formula is usually something written in the back of the exam paper, but it's actually based on the two sample sizes and the overall proportion. The overall proportion, okay, is the number of voters who are going to vote for the Conservative Party, and we're not really looking at the age groups. We're just considering them as one combined sample. We've interviewed 800 people, older and younger, and out of that 800 people, 300 of them are going to vote for the Conservative Party. So that is 0.375, which is 37.5%. Okay. Now, just as a quick remark, I tend to favor percentages as opposed to proportions. Okay. So what I'm going to do is work on the basis of percentages, which is a number between 0 and 100. Okay, as opposed to proportions, which is a number between 0 and 1. Okay, so just as a quick remark, I'm going to change that to 100 minus p bar. Okay, as long as you're consistent, it doesn't really matter. The reason is I do it is that this part of the calculation is usually a bit easier if I work in percentages, particularly if you're doing this using a calculator and a pen and paper exam. 37.5% times the complement of 37.5, 62.5. That gives us 2,343.75. 1 over 400 plus 1 over 400, that gives us 0.005. And if we work that out, it is 11.71, the square root of 11.71. So we get the square root of 11.71 and we get 3.4234. You don't have to go to so many decimal places as I do, of course. It's just, I think it just when you're trying to follow what I'm doing with a calculator, it would help you. So I don't do this in all my videos, and I realize I should. Just actually state that the test statistic is a normally distributed random variable with TZ is, just essentially standard normal distribution with 0 and 1 squared. Okay, that's just for the sake of clarity as to what TS means, actually, because just could means like TS is that T.S. Eliot the poet. I actually realize I don't do that in enough videos, actually. So just a quick statement there. Even just putting in this part here, just to sort of like be 100% crystal clear. Okay, so the general structure of test statistic is the point estimate, which is the difference in proportions, minus the expected parameter value, which is the expected difference in proportions under the null hypothesis, or the expected disparity under the null hypothesis, and it is 0. Okay. Now, in the case of one-tailed tests, it's a little bit hard to tell. It's a little bit less clear, but essentially, if it's whatever number you have written here, okay, that's really what you're looking for there. So the expected parameter value under the null hypothesis. Okay, so it's 15 minus 0 divided by 3.4234. That gives us a test statistic of 4.3816. Okay, 4.38 should be fine. 2 decimal places should be fine. Now, just a quick remark about where we get the critical value. So there's a lot to unpack with regard to critical values, and I'm just going to sort of highlight the key components here. We have a large aggregate sample size, and that's pretty much always the case when we deal with proportions. Things might be different when we have if you're looking at sample means. And in university courses, we're told to use a significance level of 5%. And just as a quick remark, that this is a one-tailed procedure. Okay, so the critical value should work out to be 1.645%. Just as a remark, that is the probability of Z being greater than 1.645 is equal to 0.05. Okay, which is our significance level. So it's just trying to work backwards. If you know this, what number would this be? That's your critical value, essentially. Okay, and that's a sort of based on the number of tails as well. So this is a one-tailed procedure. Okay, if it's a two-tailed procedure, this does not apply in the same way. You have to be a bit more complicated about it. So that is specific to one-tailed procedures. Now, also what you might do is use the student t distribution with infinity degrees of freedom. Anyway, there's a lot of work in that, finding out what critical values are. Suffice to say, it is 1.645, and I won't go into any more detail. So what's our decision? We either reject the null hypothesis or we fail to reject the null hypothesis. It's really a statement about how much evidence we have. Okay. And in this case, if the test statistic is greater than the critical value, we reject the null hypothesis. Okay, so in this case, the test statistic is greater than 1.645. 6.438 or 4.38 is greater than 1.645. We can reject the null hypothesis. That is to say, there is clearly enough evidence, strong evidence, in fact, evidence of voting of increased likelihood to vote Tory. Sorry, the Tory party or the Conservative Party. So a quick statement at the end. You don't have to write a paragraph, but just actually, quite often, what you're asked to do in a lot of questions is actually state your conclusion. Okay, and it'll be something along those lines there. Okay, so strong evidence, enough evidence, strong evidence, essentially evidence, but don't actually say proof. It's not proof. We're not proving anything. We're just talking about evidence, strength of evidence. Okay. So that's it. So that's a one-tailed procedure based on which is a bit different from what I usually do, which is two-tailed procedures. All right, we'll leave that there.